This is not so intuitively a part of buildings, but urban water systems are always center of attention for the energy they consume to provide water. And the main problem is that the pressure in the pipes needs to be maintained at some optimal level. If it's too high, you could have all sorts of problems, the most important one being that water tends to leak out of every opportunity it can get if the pressure is high. And if the pressure is too low, then external water or other things get into the system, which is not good either. And then there are debates about whether a 24/7 water system is better for maintaining the cleanliness of the water system in the pipes, or intermittent water is better, especially when you have water availability issues in countries like India, where large parts of the country actually do not have 24/7 water supply at all, right? So the ranking by 2050 is at number 71 with 0.87 gigatons of reduced CO2 by 2050. The net cost is at $137.4 billion, but the net savings are estimated at $903.1 billion. This paper talks about what is commonly discussed as the water energy nexus. Often people add food to it as well, because agriculture consumes majority of the water in most places for irrigation. So if you think about the relation between energy and water, you have energy for extraction of water, or water treatment, distribution, end use, wastewater collection, wastewater treatment, and recycling of water as well. And then for water, you have the water is used for thermoelectric cooling, mineral extraction and mining, hydropower, fuel production, and emission control. So those two are intimately tied to each other. To get an estimate of the per unit energy consumption for urban water supply, we can look at per unit energy consumption in kilowatt hours per meter cube of water. And you can see the various countries here: South Africa, China, India, and within the US averages over here at 0.51 kilowatt hour per meter cube, but California is a whopping 4.59, an order of magnitude large energy consumption per unit of water extraction. Obviously, California is very agriculture rich, very populated, very rich, and very dry, so tends to be doing agriculture in places that are actually not appropriate for agriculture, especially Southern California and so on. So there are various reasons why each country uses different amounts of energy per meter cube of water supply. Nonetheless, the leaked water from the place where it's sent into the system to where it's delivered at the end is called non-revenue water, so NRW, which basically corresponds to the water that's leaked and lost along the way. And you can see that NRW, non-revenue water, in liter per capita per day varies largely as well, and poor countries generally tend to have much higher leakages, old infrastructure, poor infrastructure. Even in places where water supply is completely privatized, the companies are apparently not very keen to fix the leaks or report the leaks, because that'll get bad attention. It's often easier to just build new systems, even if it's expensive. And consumers tend to get upset when they know that the company is losing water along the way, and they are probably paying for it. Nonetheless, here are the various numbers. Pacific Islands are very high in terms of water leakage per capita, liters per capita per day, Caucasus and Central Asia, and so on and so forth. Okay, just to keep in mind the relative loss in the system. These are the typical kinds of systems, thousands of small leaks that go undetected unless there is instrumentation along the way and constant monitoring, which is often not done very diligently. This report also provides some ways in which there is a vicious cycle of feedbacks between high level of non-revenue water slowly but constantly increasing, requiring investment in additional water production and distribution facilities to meet the increasing demand, which is happening everywhere, increased operating costs because of it, leading to increased electricity and chemical cost for treatment and so on, which leads to high capital and operating expenses and high level of commercial losses, which do not allow investing in non-revenue water reduction measures, which again leads to high level of NRW which keeps slowly increasing. A virtuous cycle is envisioned in this case to reverse the cycles, where you have continuous investment in non-revenue water management, both capital and operating expenses, which leads to NRW decreasing or being maintained at low costs or low levels, which lead to efficient operations leading to minimum water production cost and maximum revenues, which then lead to efficiency gains which can be used to finance the ongoing NRW management program. So this is considered a virtuous cycle. So in brief, modeling only the impact of pressure management and active leakage control, we estimate that water losses can be reduced by an additional 20% globally by 2050. The resulting emissions reduction from pumped distribution could be 0.9 gigatons of carbon dioxide. Total installation cost is 137 billion, and operating savings for utilities could be 903 billion by 2050. Implementing this simple solution could save up to 215 quadrillion gallons of water over 30 years. So the co-benefits here, of course, are improved water supply to many people who do not have enough or access to quality water at home. So it's not just the energy use and emission reductions, but there are massive co-benefits as well. So that's about water distribution under buildings and cities.